Hello, I'm your TA Snigdha. In this video, we will go over an overview of the project, which covers the motivation presented through an example of a lawsuit on an internet provider and the basic problem definitions necessary to solve the project. This clip is taken from WKBW TV and is on the briefing done by the New York State Attorney General, where he states that the internet provider Spectrum has not been truthful to their customers.
Spectrum Time Warner has been ripping you off. Time Warner Cable built its multi-million-dollar ad campaigns around the promise of fast, reliable internet service. But the reality is that the internet service was neither fast nor reliable. A careful analysis of internal corporate communications and tests of subscriber internet speeds showed that Spectrum Time Warner subscribers were getting dramatically shortchanged. Despite labeling its high-speed plans with names like Turbo and Extreme, our complaint quotes from internal corporate emails that show that company executives knew that their internet service was often far slower than promised.
Spectrum was alleged to have provided their customers slower speeds than what they were actually delivering. This is the overarching theme of our project, where we have to deal with providing internet service to customers while trying to achieve an outcome that the company itself desires. As seen in this chart from the New York State Attorney General's lawsuit titled Peak Hour Packet Loss, with average drop packet percentage on the y-axis and the Spectrum stats side by side with the competitor on the x-axis, Spectrum dropped their packets. The difference in packet loss percentage of Spectrum compared with the competitor is quite large, as charted. Spectrum was alleged to have used substandard routers, which led to packets being dropped. This chart is just a statistical visualization of how Spectrum tried to optimize their income by maximizing packet loss. Spectrum also maximized their income by striking a deal with Netflix. This chart, titled Average Netflix Streaming Speed for Spectrum Subscribers, with the internet speed on y-axis and time on the x-axis, it seems to be the case that Spectrum dropped its speeds during prime time so that the service providers would have to make their content more accessible despite slow internet. This, again, is just an example to show how Spectrum maximized one parameter, income, while minimizing another, internet speed. The table from the New York Attorney General's lawsuit here shown is titled NFLX bitrate impact on backbone traffic and was taken from an internal meeting from Spectrum. The table is divided into two columns for pre-Netflix deal and post-Netflix deal. In the pre-Netflix deal, the average stream rate was 2.45, but post-deal was 3.18, with increased streams from Netflix users that subscribe to Spectrum. Spectrum, according to this table, was able to get Netflix to carry their slow internet speeds, which allowed their customers to retain.
The idea of the project is for you to solve a problem where requirements are met within defined constraints. In the example shown about Spectrum maximized revenue while maximizing packet loss within the constraint of retaining customers, which they did with a Netflix deal. Problems in this project deal with maximizing revenue within some constraints for the most part. Please be wary of problem number 5 and its requirements, as it's very different from problems 1 to 4. You're now putting on a hat of an employee for an internet provider company named For Profit Only. A task of optimizing revenue for the company has been assigned to you. For this task, you will be provided multiple constraints throughout the various problems seen in this project. In general, you will have to find a solution, which in formal terms is a valid path to a client from some content provider I through for-profit only routers. Let G be a graph that depicts the connections between the content provider as seen in the root node I and the customers as seen in the colored nodes and the light blue nodes, which are the routers of for-profit company. The packets are denoted in diamond shapes. The edges between the nodes are the potential paths for data from content provider to travel through the routers to be sent to a particular client. The packet address to a client C is denoted by packet subscript C as seen here. The packets are different for each client, and the graph will be covered in more depth in example 0, where we will try to compute minimum path delays for each client node to get a feel for the graph G. Simplification.
In this project, there are no restrictions on packets received by the router, but there is only one packet per client, C. Unlike some of the other simplifications we make in this project, this is not such a big simplification. There is also no bound on incoming traffic, and we also make the simplifying assumption that the delay for each edge E is 1. To learn more about delay in the context of problem 1, please watch through the walkthrough video for problem 1. Your algorithm will choose I to C paths, and then a routing algorithm will deliver paths on these routes. Please refer to the routing algorithm video for more about this. This is not how routing happens on the internet. In particular, the TCP/IP protocol is a distributed protocol. However, distributed algorithms are out of the scope of this course.
Let P prime subscript C be the actual IC path determined by your algorithm for client C. For every client C, let D of C be the minimum D prime of C among all IC paths. And D of C is the minimum path delay that we're going to be finding in this mini example I have right here. Let there be a graph D as shown in this visual, and our task is to find the minimum path delay D of 4 for client number 4, which is the node 4, seen in green here. So we start from our content provider root node I and go to the next node 10, and then we go from 10 to 1, which would add on to the edge, making this edge number 2, and then we go from 1 to finally 4, making this edge number 3, and this is the minimum path from the root node to client 4. And there are other paths with greater lengths, but this is D of 4, which is the minimum path delay, and we computed that to be 3 in this example. Every node also has a bandwidth B subscript U, which is a bound on the number of packets it can send in each step. And payment subscript C is the money received from client C. The video on routing algorithm will explain how the routing delay, capital D of P subscript C, is computed. It is important to know distinction between minimum path delay D of C to be not equal to the routing delay, which will be discussed in the routing algorithm video. Let's compute minimum path delay.
Similar to what we've seen before, let's start from the root node and go to the router node of 10. And then from 10 to client 1. So what do you think
the minimum path delay
of the packets is from root node 0 to client 1?
We will be excluding the part where the path is greater than 2.
So D of 1 is actually 2. And to compute something similar for node number 7, which is the client, we will go through an extra edge to get to 4, and finally 4 to 7 as seen in the visual here, making D of 7 to be 4.
Again, excluding paths of length greater than 4. The minimum path delay values will be used to define revenue functions in subsequent problems. Bandwidths that are seen here are needed in the routing algorithm, so please refer to the routing algorithm video to learn more about the need for them.
As an overview of the project, your goal is to compute I to C paths while maximizing revenue under some constraints. And note that I is the root node and C is the client node. An overview of problem 1 is dealing with maximizing revenue on G. We will discard the bandwidth here and assume it to be very large, and instead attach a revenue for each of the client. And the goal for you is figure out a path from root node I to any client such that the revenue is maximized. Refer to problem 1 walkthrough video for more details. An overview of problem 2 is that it is similar to problem 1, but has limited bandwidth instead of it being infinity. And for problem 3, it is an addition of whatever you solved in problem 2 plus an extra parameter, which is called the complaint threshold. As you can see, there's a pattern of more and more constraints being added as we go through the problems. Please watch the problem 3 walkthrough video for more details on these additional constraints. And an overview of problem 4 is very similar to problem 3, but now each of the client has a certain priority defined on top of the bandwidth constraint and the revenue constraint and the threshold constraint. And finally, the overview of problem 5 deals with no complaining clients. And it is quite crucial for you to note that problem 5 is very different from all the problems that you've seen before. There's a different penalty and different revenue definitions, as this algorithm is for a different company called the Ethical Internet Company. Problem 5 basically runs along the stories of you switching over from for-profit only company to ethical internet company. Therefore, you're assigned a completely different constraint to maximize
Revenue.
that the ethical internet company wants. So please be mindful of the different constraints and definitions for problem 5. And as always, refer to problem 5 walkthrough video for more details. And a final few words on this project as a whole. You are required to have groups of size 3, and the same group should solve all the problems. And some suggestions are, please start early, and it is easier if you stick to one consistent programming language. There are also no optimal algorithms known, so please do not worry too much about runtime. Optimizing runtime is not the main objective, and it is suggested that you do not spend unnecessary time on it. And that would be the end of the entire project overview. Please do remember that the TAs and the course staff and the Professor Autry is here for your success. And we are always happy to help you out whenever you need help with something, regardless of what the question might be, even if it's a simple question that might have been answered already, or a quite complicated question that might take a good chunk of time to answer. It doesn't matter to the teaching staff. We only want to help you out, so we will gladly take any questions from you related to the course content and try our best to help you succeed. Thank you very much again.